Hi, everybody. Welcome back to Dave's Math Channel. I'm your host, David Tear, and today I'm doing another feature on a daily math problem that I posted a couple days ago. This problem concerns something called ABC triples, and I'll get into that in a second. And the formula in the middle, this is a formula for what's called the quality of an ABC triple. I'll get into that too. Anyway, let's be. So first I have to tell you what the problem says. So here's the problem. First I'm defining an ABC triple here. So I say an ABC triple is an ordered triple, A comma B comma C, of coprime positive integers. That just means they don't have any common prime divisors, any common divisors. Um, for definiteness, we say A is less than B, and A plus B equals C. So C is just the sum of A and B. But not only that, it also has to be true that C is greater than what's called the radical of the product ABC. So now I have to tell you what the radical means. I know there's a lot involved in this problem, but this is actually a very important problem. That's why I'm going over this. So radical of n, where n is an arbitrary positive integer, rad n, is just the product of all the prime divisors of n, where we just take one power of each prime divisor. It doesn't matter what power there are in n. Another way to say that, it's the largest square-free number that divides n. So there's no squares, not trivial squares that divide the radical. Um, so for maybe I should give an example, like the radical of 4 is 2, because 4 is 2 squared, or the radical of 6 is 6, because 6 is square 3, 6 is 2 times 3, but the radical of something like 100 is 2 squared times 5 squared, the radical of 100 is 10. Anyway, those are just some simple examples. So now I've told you what an ABC triple. Oh yeah, I didn't quite tell you yet. So the quality is this formula on the bottom of the slide. Q of ABC is the logarithm, the natural logarithm C divided by the natural logarithm of the radical. I think I did say the problem. I said C has to be greater than the radical. That means the quality is greater than 1. And just to tell you what an ABC, so I've already said what the problem is. Oh yeah, I haven't said the problem yet. I want you to look. The problem is to find all ABC triples of the form A is 1, and B is n squared minus 1, and C is n squared. N is a arbitrary positive integer less than or equal to 100. So I want you to find all of those ABC triples. For some values of n, this will be an ABC triple. For some of them, it won't. Um, anyway, so why is this an interesting problem? I just stated the problem. You might wonder, why do we even care about this stuff? Well, there's a very important unsolved problem in number theory. This is actually considered one of the most important unsolved problems in number theory, pretty close up there with, I'd say, the Riemann hypothesis. This is called the ABC conjecture. And I believe this was first conjectured around 1985. So it's not really that old a problem, but it's stifled, it's stumped mathematicians for the last 40 years. Nobody's able to prove it yet. But what it says, the ABC conjecture says that for every epsilon greater than 0, mathematicians seem to like epsilon. It's used in proofs of limits. It's used a lot in calculus. But it says that for every positive number epsilon, no matter how small, there's only a finite number of ABC triples such with quality greater than 1 plus epsilon. And the reason we need epsilon here, it's not really true, surprisingly. It's not true if we let epsilon be 0. I mean, the way I define an ABC triple above, I just said the quality has to be greater than 1. If you define an ABC triple that way, then actually you can prove pretty easily that there are infinitely many ABC triples. I think you can even find sequences of ABC triples with a pattern of, where epsilon approaches 0, the quality approaches 1. But you do need a finite non-zero value of epsilon. And the conjecture is only finitely many for every value of epsilon, even though there's a lot of them. I think I've seen tables on this, and there's like I think there's something like um, there's over 10,000 known ABC triples. I think with epsilon um, equal to 0.05. And I think the biggest value of epsilon that is known is about zero point 0.6. I think there is an ABC triple. I don't remember what it is, but there is an ABC triple with a quality of about 1.6. And there's already, I think, several hundred with a quality of over 1.4. Anyway, I've seen tables on this. I have another video on the ABC conjecture. I recommend you guys watch it if you want to learn more about it. But anyway, I've just stated the problem, and I don't know any better way to solve this problem than brute force. There probably is a systematic way to solve a problem like this, but I don't know what it is. I haven't done it systematically or analytically. I just did it using brute force. With n equals 100 is pretty easy to do. So here's the code I wrote. Again, I wrote Mathematica code to solve this problem. And, there's two functions I wrote here. There's a very simple one-line function I just called rad. Rad of n, that's the radical of n. That's just the product of all the prime divisors, and the way you can get the prime divisors in Mathematica is you can use one of their built-in functions called factor integer. That'll give you the prime factorization. It gives you as a list of pairs of numbers, p comma e, where p are the prime divisors and e are the exponents. So you just ignore the exponents. That's what this all comma 1 means. You just kind of scoop up all the prime divisors of n, and then you multiply them all together. That gives you the radical. And then here's my code below. Pretty simple code. One for loop. So we're just doing a for loop over n. That's the number we're squaring. And I call it square n2. N2 is just n squared. I think you can see that line. And max, that's the thing we're going to set equal to 100, but you can set it to equal to whatever you want. I just did it up to 100. And then, you calculate the radical of n squared times n squared minus 1, because that's ABC. Remember, A was 1, B is n squared minus 1, and C is n squared. So the radical, the thing I'm calling small rad, is just the radical of n squared times n squared minus 1. That's the line in the middle. And then you just check whether the radical is greater than C, which is n squared, n2 as I'm calling it here. And if it is, or the radical has to be less, actually. If the radical is less than n squared, we add it to our results. And that's going to give us a table of all the solutions. And what I put in this table is I put the value n, and then c is n squared. That goes right next to it. And then the third column, we have the radical, which should be less than n squared. And finally, we have the quality in the fourth column, which should be greater than 1. So let's see what we get when we do this. Here's my results. I kind of broke it down into two tables. It gave me a single table, but I kind of edited it here to make it look a little nicer. But you can see I got 19 values of n, and here they all are listed out. In the first column are the values of n. A little haphazard, I guess, but they seem to get a little rarer as n gets larger. And then I have n squared right next to that, and n squared can be as big as 10,000 since n is going to 100. And then in the third column, I have the radical, which you can see for all these examples is less than n squared, as it must be. And finally, in the fourth column, I have the quality. And you can see the qualities are all greater than 1, meaning these are all ABC triples. And it looks like the one with the biggest quality is for n equals 49. So that'll be the ABC triple 1, comma 2400, comma 2401. The radical in this case is just 210. That's 2 times 3 times 5 times 7. You can check for yourself the radical, the product of 2400 and 2401 is just 210, because neither of those numbers has any prime divisors bigger than 7. And the quality in this case is a pretty high quality. This one's 1.545667. So it's kind of unusual to see ABC triples with that high quality. But I guess one of these does have that high quality. So anyway, so that completes my video on the solution to this problem involving ABC triples. Thank you for watching. Long live math, and I'll see you guys next time. Bye.